In this video, we are going to find all integers n such that 8n minus 25 all divided n plus 5 is a cube of a rational number. Before we move on, don't forget to give a like, subscribe to our channel, and turn on post notifications. To solve this equation, I'm going to rewrite this cube as, say, p over q all cubed. So p over q is the desired fraction, the rational number, and there are some restrictions, which is that p and q are integers that do not share any common prime factor. I call that coprime. And the denominator q is non-zero. So next I'm going to write the left side as 8 minus 65 divided by n plus 5. It's just a quick division. So the fraction will become easier. Then moving the p cube over q cube to the left and 65 over n plus 5 to the right. And simplify, cross multiply. We will have 65q cubed is equal to n plus 5 times 8q cubed minus p cubed. We can factorize that with the identities of the difference of cubes. And we have 2q minus p times 4q squared plus 2pq plus p squared. Now for the left, it's just constant times the power of an integer. Notice that for that integer q, it's coprime with the other unknown p. So for these two expressions, 2q minus p and 4q squared plus 2pq plus p squared, they are supposed to be coprime with q as well, because with the terms minus p and the terms p squared, we know that it will not share any common prime factor with q. So that means if this product has to be a multiple of q cubed, then that means n plus 5 itself must be a multiple of q cubed. So that means this part is a multiple of q cubed. And so that means the remaining parts, the colored parts, 8q cubed minus p cubed, is a divisor of the number 65. So that means 2q minus p multiplied by 4q squared plus 2pq plus p squared is a divisor of 65. A very simple composite number, 5 times 13. So we can start analyzing the factors of 65. Notice that for this part, the quadratic part of the product can be written as p squared plus 2pq plus q squared plus 3q squared, which is p plus q all squared plus 3q squared. So that means for this part, which is an integer, it's supposed to be written as a square plus 3 times another squared. And it has to follow some properties, which is that, in particular for mod 3, because we have a 3 as coefficient here, it must be congruent to a square mod 3. And that is either 0 or 1. So when we look at the factors of 65, which are 1, 5, 13, and 65, we can quickly eliminate 5 and 65 because they cannot be congruent to a square mod 3 at the same time. And so that means p plus q all squared plus 3q squared cannot be 5 or 65. Of course, we can't take negative values because they are sum of squares. And also it can't be 1 because we know that q is non-zero. So this tiny bit is at least 1. And that means the whole thing will be at least 3. So that means we have only one way out, which is p plus q all squared plus 3q squared is equal to 13. Now for this, we still have some possibility because when we take mod 3, it's still possible to have a solution. And indeed, to solve this, the only possible integer solutions are when 3q squared equals to 12. We can first bound it by 3q squared is less than or equal to 13. So then you are more convinced that 12 is the only option. So then 3q squared is either starting from 3, and then the next one is already 12. So if 3q squared equals to 3, then the other squared will be equal to 10, which is impossible. But for the 12 case, it has to be 1. So now for 3q squared equals 12, we have q equals 2 or minus 2. And then for p, we have p plus q all squared equals 1. So p plus q is equal to 1 or minus 1. We can still have two possible solutions for each case of q. When q equals 2, we either have minus 1 or minus 3. Or when q is minus 2, then p is either 3 or 1. So therefore, pq have these 4 possible cases. Next, we can put it back to the other part of the product, which is this 2q minus p. This part is supposed to be also a factor of 65. So let's try what happens when 2q minus p. For these cases, 2q minus p equals 5, equals 7, equals minus 7, and equals minus 5. So we can also reject these two cases and go back again. We have two candidates left, minus 1, 2, 1, minus 2. We have to test whether it satisfies the original equation. Let me go back again and check. It's minus 1, 2, and 1, minus 2. So for the first case, minus 1 over 2 all cubed, that's minus 1 over 8. So that's 8 minus 65 over n plus 5 equals minus 1 over 8. So 65 over n plus 5 is equal to 65 over 8. So that means n equals 3. For 1, 2, we can skip the next step because it's also minus 1 over 8. And so that means, again, we have n equals 3. So n equals 3 for both cases. That means our final solution is just n equals 3. This is the final answer. Please feel free to share ideas in the comments. Thank you for watching. See you next time.